All right. So wastewater. We've looked at this graph before in reference to drinking water, beginning chlorination. That's a good thing, right? What we can recall is that really diseases like this, the typhoid fever, we're really trying to disrupt the fecal-oral route of transmission. And typhoid fever is transmitted that way. So wastewater plays a role in that, right? It's not just treating our drinking water. That is clearly important, and if we did it perfectly, that would be great. But there's still some other factors. What about the food we eat? What about if we were to use water to irrigate some crops and then eat the crops? You know, are we contaminating our food? What about swimming and things like that, right? So there's important reasons that why wastewater treatment can also contribute to control of that fecal-oral route of transmission. Some rather unpleasant wastewater scenarios here. This is a few pictures I took 10 years ago in a trip to Nicaragua. Here we have an open, unregulated mercury, or gold mining operation using mercury. So in this little spot here, they've got this little grinder churning around, just mechanically mixing a slurry of soil, of ore, with a bunch of mercury. So they're trying to amalgamate the gold from it. And they do have a little bit of a catch basin there to probably collect as much as they can, mostly the gold and stuff, but there's certainly going to be a lot of mercury just running straight off back into the environment. So quite an issue, and these are actually kind of everywhere. I went this past March and we saw one right by a river, just plugging along. Lots of people working there. So, you know, there's a lot of reasons we care about wastewater. This image at the bottom is kind of a crazy one, this neon green water. That's a wastewater stream. It was discharged, and it was discharged into a landfill, and now it's etching its way through the landfill, and then heading into a river from there. So talk about contamination, it's quite contaminated. It's super green because it was something of a wastewater stabilization lagoon type of thing, so it has a lot of algae in it. So the green is not necessarily the awful part of it, but it kind of gives the feeling of it, right? So it's pretty serious and obvious reasons why those are not so good. So thinking of kind of big picture about where we are with water and wastewater treatment, we've kind of covered a lot of the usage, right? Where do we get it? How do we send it to our users? Maybe there's industries. Now we're going to take a look at the wastewater side, and keeping in mind that wherever we're discharging into a surface water, there's likely going to be somebody else that's going to be taking it later to use that, right? So we want to, because there's a wastewater treatment site somewhere up here feeding into what they're taking, you know, we want to be protective. What we'll find is protect the intended uses of the receiving water that's going to take the wastewater. It's got to go somewhere. You know, we can't just make all the waste disappear magically, right? So we've got to do something with it and send it somewhere. So we're going to talk a lot about the secondary treatment aspect of wastewater. I have a few things to talk about for primary treatment. We've already covered a fair bit in the sense that we've done sedimentation, right? So one thing to keep in mind is in the class overall, we've covered some physical processes, sedimentation being one of them. We've covered some chemical processes, so what we would do with disinfection, for example, directly relevant to our wastewater treatment. What we haven't really touched on much yet is biological processes. So if you want to think of it that way, we've kind of broken up the class into physical, chemical, and biological aspects of wastewater treatment, or of water and wastewater treatment. Okay, so that we're going to tie things together a bit in that manner. I'm only going to get partway through today of my intro, and next time we'll pick up with a bit more on kind of the regulations and maybe a couple examples of the screen and bar rack before launching into secondary treatment, which primarily involves some form of a bioreactor. We are feeding microbes as much oxygen as we can because we want them to feed on all the junk that's in the water, right? If we have dissolved molecules, proteins, fats, lipids, sugars, whatever it is that microbes could eat, we want them to be eating it as much as they possibly can so that we convert something that is dissolved. It's pretty hard to grab one molecule out of the water and convert that into a cell, because cells, bacteria cells, can then clump together. Then they could settle. You could grab them, you could filter them. It's a lot easier to handle a cell than it is to handle one little sugar molecule floating around, right? So the concept here, in some sense, really goes back to that thing I showed you the first day, right? We send some water through a process or some media, something happens to it, and now we have a little pile of stuff, right? That's kind of what we're trying to do, right? And the process here largely relies on the bacteria eating the stuff, creating more cells, right? So this is a cell factory, we could call it. Typically, we will use a aerated system. That's kind of the conventional. That would be a waste-activated sludge. So cell factory is my silly term for today, but typically you'll call this waste-activated sludge. So if you ever see that terminology, it's activated because we are feeding it oxygen. It's sludge because we're creating a slurry of cells and bacterial mass and whatever else might still be in there. And it's wastewater, right? So then what we do with that is we send it through clarifiers. Clarifier and sedimentation basin are essentially synonymous, but in wastewater, it's more often referred to as clarifier, for whatever reason. So what's going to happen is, if things are working well, then we'll create a lot of bacterial mass that we can settle a lot of that. So we'll settle a lot of bacterial mass, then be able to recycle it, in part to keep lots of bacteria in the influent. Because if we were just to dump all the bacteria every time and get rid of them all, we have to start from zero, whatever happens to be in the pipes. There's going to be some bacteria in the pipes for sure, but it's not at a high concentration like we want it for the bioreactor to be doing a lot of food consumption, right? We want a high amount of bacteria there, so we manage that pretty carefully. Some of it is sent to sludge processing. Talk a little bit more about that later. Of course, we're going to get some here as well. This will include more than just bacteria. That'll be other junk. So we'll recycle this nice bacteria mass that we've created, or a portion of it, and then that's not going to get rid of all of the bacteria, but on a mass basis, the mass of bacteria that we're handling, we'll actually talk about it as milligrams per liter of bacteria stuff. So on the scale of wastewater treatment, we do grow so much of it that we will often refer to this as like milligrams per liter of volatile suspended solids, VSS, or sometimes mixed liquor suspended solids. We'll come back to these terminologies as we get to them. But basically we can weigh it out because we have so much of it. Now that doesn't mean there's no bacteria left, right? If we can settle it, there's still some free-floating bacteria there, so we have to do some disinfection. Probably some viruses too, right? Whatever was coming through the system, this bioreactor, maybe some of the viruses were eaten by bacteria or something, but chances are there's going to be some viruses left, right? So having a disinfection step is good if we are concerned about that for public health exposure. Some countries don't disinfect their wastewater. France, for example, is starting to think about doing so, but conventionally they haven't. All right, so that's kind of the big picture. This would be a typical wastewater treatment setup for a municipal plant. Secondary treatment is generally considered a biological treatment plus a clarifier, something to grow lots of bacteria and then to separate them back. We can add in the disinfection step as part of that, but I would say if we add any tertiary, it would probably go here. So we might add tertiary treatment, and then the disinfection, we'd still need disinfection, but it kind of throws a wrench in like how you distinguish them all. Tertiary treatment would be something like nutrient removal, or if there was some specific issue that maybe receiving water had to have especially clean in some particular manner. Maybe if we had to do pH adjusting, that probably wouldn't even be counting here. But if we have maybe some fancy anaerobic, aerobic cycling, that might be constituted here. So we could say phosphorus, nitrogen removal, steps like that. Sometimes you might have a specific step maybe to try to convert ammonia into less harmful things. The more advanced stuff, we're not going to spend too much time on that. I'll give you a few examples of the types of things that can be used, but generally that would happen after the primary consumption of the waste. So the initial bioreactors, we're trying to get lots of the carbonaceous waste, lots of stuff that would demand oxygen. Okay, so our wastewater regulations are really designed, like I said, based on the idea that we want to protect intended uses. Oftentimes that means it's going to be like the receiving water itself will determine what treatment we need. So if it's a very pristine river or stream, it's not going to be able to handle the same amount of ammonia in it without impacting the wildlife as the Mississippi would down here, right? If we're talking about a tributary to the Mississippi way up north, maybe that system is ecologically very vulnerable to a bit of ammonia or a bit of oxygen demand. Here, there's just so much stuff in the Mississippi by now and so much water that when the South Baton Rouge wastewater treatment plant discharges to it, sometimes it's an improvement to the water quality, according to certain metrics, right? So their goal is kind of like to not be as bad as the Mississippi. So they kind of have a funny situation there. But so some of the regulations are based in part on the receiving water. Some of them we have just minimum standards. And some of the permits and things will be calibrated accordingly to what's needed. So the EPA, for surface water discharges, they have the NPDES system, and they delegate that to most of the states. It's an option for the states to, through maybe DEQ, for example, to establish their own local regulatory agency. I think there's a couple still that haven't done that, so it's the EPA, I think Arizona maybe, regulates them directly. The benefits to having a local presence is locals know locals, right? And so there's maybe a little more trust and things like that. So this National Pollutant Discharge Elimination System, I actually, when I finished grad school, the first job I was able to find was as a NPDES permit writer. So some of the experience I'll share with you today and next time is kind of coming from that. The ultimate goal of it, as we'll see, was to reduce and eliminate discharges of pollutants to surface waters. Initially, they wanted to eliminate all pollution. Turns out that's not actually practical, and we'll talk more about that. One of the things we might miss, if we're thinking about regulations in general, one of the big benefits this regulatory framework provides is a safety net for industries to pollute. That sounds pretty funny when I say that, right? It's like, we're intending for them to pollute? Isn't pollution bad, right? Well, it turns out we could consider temperature high temperature or low temperature as a pollutant. So if you take a power plant and it's essentially bringing in a lot of cold water to act as a cold water reservoir for the thermodynamics, right? Carnot cycle kind of stuff, right? You have the hot reservoir and a cold reservoir. That thermal difference will drive our energy production, essentially, a way to drive that. And so when we heat the water, using it to cool, as that cool sink, that's elevating the temperature. And what's the big deal maybe? Especially if we discharge it at a decent temperature, it's not like boiling. Well, it's going to hold less oxygen. So even just the amount of oxygen the local environment can contain, then we could consider the temperature itself as a pollutant. So are we trying to eliminate all pollution? Actually not, right? It is to our benefit to be able to pollute, but it is also to our benefit to be able to control our pollution in a way that's protective of intended uses, right? So one of the things that, let's say for a moment, I decided to start a small business creating bottles, right? Plastic bottles. And I use some chemistry and chemicals and stuff. And in washing off the bottles or something, some of those chemicals get into the wastewater, right? I have a wastewater stream now of water containing some plastic chemicals. Might be bad, might not be bad, right? As a small business owner, I certainly do not have the required facilities to test whether or not that's toxic, to test how much is in there. Maybe I could do that, perhaps. To know whether or not my discharge of this into the environment was the reason Sally's dog died. But Sally's now trying to sue me because she thinks it did, right? So if I have to then publish my own scientific studies or pay for them or whatever, do all of that to confirm that no, my plastics is not what caused some sort of harm in the environment, that's way too much of a burden. Nobody would ever be able to do that. So there wouldn't be any people producing plastic bottles, for example, or there would be really difficult limitations there. So regulations, these permits, are actually quite protective of industries in a way. Of course, there's frustrations industries will have for, it's too difficult to owners or whatever. But what it's doing is it's providing a license. Like, you have a driver's license. You are permitted to drive a vehicle on the roads. It's a permit that you're given, can be revoked. That's what these permits are. It's a permit that's given. Anybody's eligible to apply for them. There shouldn't be any discrimination or whatever to say no, you can't. But so long as you're following that permit, it's on the EPA if your discharge harmed somebody, right? So then the EPA is sued if somebody's being hurt by that. So it's interesting. It's interesting to think about the fact that these permits can actually be protective and encouraging of industries because of that protection. Now, clearly, I think, especially in Louisiana, we hear probably a lot, there's probably a lot of people that are dealing with permit issues all the time in industries and stuff. So there's certainly room to balance. There's certainly important cases if they're not followed, or people are getting away with not following them, or if the permits themselves are too lenient, allowing too much pollution. All of that is involved in this, right? So I'm not making a statement that it is protective always or is never any of that, but all of that's kind of built into the aim here, and we can kind of understand what it does for us a little better looking at it that way. Okay, so I'll end there for now, and we'll pick